Today we're going to be proving the famous Pythagorean theorem. The theorem states that given any right triangle with legs A and B and hypotenuse C, that a squared plus b squared equals c squared. This is a relationship with which you're probably already familiar and have even used before, but why is it true? That's what we intend to figure out today. First, let's understand the diagram, understand what we're given, and of course what we have to prove. We're given a right triangle. We're going to call it ABC. We're going to put the right angle at C. We're going to use the lowercase letters A, B, and C to represent the sides of the triangles, and we're going to put the lowercase a opposite the uppercase A, and the lowercase b opposite the uppercase B, the lowercase c opposite the uppercase C. This is a common geometric convention to keep diagrams consistent across multiple authors. Of course, we have to prove that a squared plus b squared equals c squared. The proof starts with the construction of what I call the third altitude. I call it the third altitude because the first two altitudes are the legs of the right triangle, BC and AC. We construct this altitude, CD, perpendicular to the hypotenuse AB, and it cuts the hypotenuse into two smaller segments. We're going to call it little d and little e, as shown in the diagram. An interesting observation. The altitude that we just drew creates two right triangles, both of which can be proven similar to the whole right triangle. And if both of those triangles are similar to the same triangle, then it would make sense that they're both similar to each other. So let's get to proving the triangles similar. While we've used multiple methods over the year to prove triangles similar, angle-angle is what's going to help us best. So if we look at triangle ABC and triangle ACD, clearly they both have a right angle. So that will be our first angle in angle-angle. And they share angle A, because if we look at triangle ACD, it's that lower right triangle. And it's the exact same angle as in the big triangle ABC. So those angles have to be congruent because they're shared using the reflexive property. So we can state that triangle ABC is definitively similar to triangle ACD by angle-angle. We use a similar process for triangle ABC and triangle CBD. They also have right angles, and they share angle B. So using the reflexive property, with angle B congruent to angle B, we have those two triangles, ABC and CBD, similar by angle-angle. We now have two triangles that are similar to the same triangle. The two triangles CBD and ACD, we have both proven individually similar to ABC, so therefore triangle CBD and triangle ACD must be similar. Great. The question now becomes, how can we use similar triangles? It's their definition, and specifically dealing with the proportionality of the sides. How can we use that to help us get to the Pythagorean theorem? Well, let's look at triangle ABC and triangle CBD and what proportions we can write. If we look at the ratio A over D, A and D are both short legs of different triangles. Segment A is the short leg of the big right triangle, and segment D is the short leg of the smaller right triangle. So A over D, they are corresponding sides, so we can write them that ratio. We're going to set that equal to C over A, because C over A is the ratio of the hypotenuses of those triangles. C is the hypotenuse of the big right triangle, and A is the hypotenuse of the smaller right triangle. So if we cross multiply, A squared is equal to DC. If we use a similar process with triangles ABC and triangle ACD, we can write the proportion B over E equals C over B. That's because B and E are both long legs of the two different triangles, B of the big triangle, E of the smaller triangle. And C over B, C and B both represent the hypotenuses of two different similar triangles. C is the hypotenuse of the large right triangle, and B is the hypotenuse of the smaller right triangle in comparison to the two that we're looking at. So if we cross multiply there, B squared is equal to EC. So now we need to put together a plan to actually prove the Pythagorean theorem. We have lot of things, but how can it all be put together? Remember, we have to get that a squared plus b squared is equal to c squared. We have an expression for a squared, and we have an expression for b squared, so if we add those two expressions together, it would certainly be a step in the right direction. So let's do that. Since a squared equals dc and b squared equals ec, we can write that a squared plus b squared equals dc plus ec. Notice there's a c in both terms on the right-hand side, so we can factor out that c, leaving us with a squared plus b squared equals c times the quantity d plus e. But what's d plus e? Let's take a look at the diagram. D plus e adds up to the hypotenuse, which is c. So if we substitute that in, a squared plus b squared equals c times, and instead of d plus e, we're going to write c. So we have c times c on the right-hand side, which we can write using just simply the laws of exponents as c squared. So we've done it. A squared plus b squared equals c squared. This is fantastic. We haven't assumed that the Pythagorean theorem was true to get to this. We actually started using only the rules of right triangles and similar triangles, and we have generated the Pythagorean theorem to prove it beyond a shadow of a doubt. This is one of hundreds of proofs of the Pythagorean theorem. Because the Pythagorean theorem is so famous, mathematicians and even professional and amateur are always looking for new ways to prove the Pythagorean theorem because it's so useful and just so famous and has been around for so long. But this is one of my favorites. It's very attainable for high school geometry, and it really deals nicely with similar triangles and the laws of right triangles in order to arrive at the famous conclusion.